Hello everyone, welcome to Brain Blitz Audios. Today we're going to be looking at NEET preparation, and this series deals with previous year questions of medical entrance examinations in India. Today we'll be looking at the chapter Classification of Elements and Periodicity in Properties. This is the third chapter in the grade 11 syllabus of chemistry in CBSE. Now this chapter is really short, and therefore the questions that accompany it are very easy as well. However, they require concept knowledge. Let's jump into our first question. This is our first question. The first ionization potential is maximum for A. Lithium, B. Uranium, C. Iron, D. Hydrogen. How do you solve this question? It's important to know the definition of the ionization potential, which is also known as the ionization energy. So ionization potential or ionization energy refers to the amount of energy which is required to remove an electron from any isolated atom or molecule. So the energy required to pry an electron away from an isolated atom or molecule is referred to as ionization energy. And when we talk of the first ionization potential, so that refers to the amount of energy to remove the first electron. Now, when it comes to electrons, the lower value of the shell number or the principal quantum number, which is represented as n, would give you the idea that the electron is closer to the nucleus. And when it's closer to the nucleus, it is more attracted towards the positive center. So it needs more energy. It requires more energy to be ionized. So for the atom to get ionized, the first ionization potential will be high if the value of n is equal to lower values, because lower values imply that the electron is closer to the nucleus. So let's look at lithium. The valence electron lies at 2s1. So therefore, for lithium, n is equal to 2. What about uranium? The uranium electrons come in the 7th shell, and therefore the value of n is equal to 7. What about iron? Iron is a d block element, and therefore it starts its journey from n is equal to 4. So n is equal to 4 is the orbit from which the d orbitals start coming. So therefore, when n is equal to 4, the valence electron of iron is present. So when it's present at n is equal to 4. But hydrogen has only one electron, and that one electron is present in its first shell. So for hydrogen, the electron has the value of n as 1. Now notice which of these has the least value? Hydrogen. So that means the valence electron of hydrogen is closer to the nucleus. So therefore, you require more energy to pry an electron, the valence electron, away from hydrogen than, say, uranium. So that means hydrogen, option D, has the maximum first ionization potential. So option D is the right option. Let's move on to the next question. Which element has high electron affinity? So here it's key to know what is the term electron affinity. So in the periodic table, every element wants to reach stable configuration. So electron affinity is the affinity of an element in order to accept electrons. So when elements have high electron affinity, it means that these elements want to gain electrons in order to reach the stable electronic configuration. So what basically means is that elements which want electrons from other elements are the ones which have high electron affinity, like the elements present in group 15, 16, 17. So it's just enough to look at the group of the given elements. For option A, sodium lies in the first group, and the first group contains alkali metals. These want to give away their spare electron instead of accepting one. So option A is incorrect. Option C and option D, which is beryllium and calcium, both want to give away 2 electrons in order to reach their stable electronic configuration. So they won't have high electron affinity. C and D are incorrect. And these are present in the second group, the alkali earth metals group of the periodic table. Option B is the only remaining option, and chlorine, which is option B, is present in group 17, which is part of the halogen group. And among the halogens, chlorine has one of the highest electron affinities. That's why option B is the right option. Chlorine is the element which has high electron affinity among the following. Now, we're asked to find out which group of periodic table contains no metal. Now, in the IUPAC system, the periodic table is differentiated into 18 groups. However, in the old version, we have a different numeric system. And we are asked to find out which one of these numbers represent a given group of periodic table which does not have any metal. So no metal should be present. So the number 1A represents the first group, which is alkali metals. Now A refers to the S and P block elements, and B usually refers to D and F block elements. So that is the way in which we used to classify elements and their groups earlier. So first group is alkali metals, so all of them are composed of metals, so option A is incorrect. What about option B, 3A? Now, we told you that 3A would represent any group which has S or P block elements. In this case, 3A would represent group 13, which has metals such as aluminium, gallium, etc. All of these are metals. Option B is incorrect. What about option C, 7A? Now 7A would represent group 17, which mostly contain halogens such as fluorine, chlorine, and bromine, etc. However, we do not know the state of the element tennessine, which is the 117th element. So therefore, this casts a bit of a doubt. However, if you look at option D, which is group 8, this refers to the 18th group of the periodic table, which contain noble gases. And all of these are gases, so that means there is no trace of any metal whatsoever. So option D will give us the right option. The reason why C is becoming incorrect is because option D contains of noble gases only, and therefore they don't contain any sort of metal. However, as we go down the halogens, the latter parts of it would have some sort of metallic properties, which is why we chose option D, because the 18th group will have a stable electronic configuration always. That's why they are inert. Let's move on to this question. Which of the following is the atomic number of a metal? We're given the atomic numbers 32, 34, 36, and 38. So it helps to write the electronic configuration given. So for 32, we'll write the electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p2. So 2 plus 2, 4, plus 6, 10, plus 2, 12, plus 6, 18, plus 2, 20, plus 10, 30, plus 2, 32. Now, this number, the atomic number 32, is the atomic number of germanium. The element germanium is a metalloid and not a metal, which is why option A can be classified as incorrect. What about option B, the number 34? Now, 1s2, 2s2, 2p6, 3s2, and 3p6 all constitute the electronic configuration of argon. And so when we're writing elements which have atomic numbers higher than argon, we use the notation argon first to denote till 3p6 and then continue our notation. This makes the notation easier. So then we have 4s2 makes it 20, 3d10 makes it 30, and 4p4. So this configuration is present for selenium, and selenium is again part of the group 16 of the periodic table, which contains nonmetals such as oxygen and sulfur. So that makes option B incorrect. What about option C, 36? So again, we'll start off with argon in order to simplify, and then we have 4s2, 3d10, 4p6, and that completes our configuration. Now this is present for the noble gas krypton. So a noble gas is not a metal, so option C is incorrect. Now for option D, we can, instead of putting argon, we can put krypton because krypton is the closest noble gas. So krypton and then 5s2. And 38 is the atomic number of strontium, and strontium is present in group 2. Group 2 is alkaline earth metals, so that makes option D the right option. After analyzing the electronic configurations, we've reached that option D is the right option. And if you knew the atomic numbers, you would get the elements themselves, which would also lead you to the right answer, which is option D. Because germanium is a metalloid, selenium is group 16, so it's not a metal. Krypton is a noble gas, and strontium, which is our right answer, is part of the alkaline earth metals group. So it is the metal. Let's look at this question. The correct order of hydration energy of alkali is Li plus is greater than Na plus is greater than K plus is greater than Rb plus, and we have other combinations. Now we need to find out which of these is the right one. So how do we connect the hydration energy with alkali? So the relation for hydration energy is inversely proportional to the size of an element. And in a group, the size increases down the group, which means that the hydration energy will decrease down the group. So lithium will be the smallest of the alkali, and therefore it should have the highest hydration energy. And then we'll have sodium, which is the next smallest. So that means the next highest energy will be sodium. Potassium takes third, and rubidium takes fourth. If we're allowed to extend it, then cesium takes last. So this is the correct order. Now, if you're presenting it as ions, then Li plus is greater than Na plus, is greater than K plus, is greater than Rb plus. Again, since all of them are of the same group, they have the same kind of ion, which is +1. So this configuration is present in option A. Now, if you're looking at the other configuration, the option B says that rubidium has the highest. So that says that rubidium will have the least size. However, it is down the group, so that is incorrect. Again, sodium is actually bigger than lithium. It has more atomic radii, so option C is incorrect. Potassium also has the same problem because it's present lower in the table, so option D is incorrect. The right answer is option A. Lithium plus is greater than Na plus, greater than K plus, greater than Rb plus. And we used this relation that hydration energy is inversely proportional to size. And we also used the other property that in a group, size increases as we go down the group, which gave us the right option. Li plus greater than Na plus, greater than K plus, greater than Rb plus. Let's look at this question. Sodium forms Na plus ion, but it does not form Na2 plus ion because, and we need to find the reason. Very low value of first and second IE stands for ionization energy. Very high value of first and second ionization energy. High value of first ionization energy and low value of second ionization energy. Low value of first ionization energy and high value of second ionization energy. So sodium has the configuration 1s2, 2s2, 2p6, 3s1. So if we take one electron from sodium, you get Na plus, which has the same electronic configuration as neon. Neon is a noble gas, so this is stable. So when we remove this electron, you get a stable configuration. So therefore, the first ionization energy will be low. And since we found that out, we can eliminate options B and C, which says that the first ionization energy is high. What about the value of the second ionization energy? Now, Na plus has the same configuration as neon, which is stable. However, if we were to remove another electron, it will be difficult because then the configuration will be that of fluorine, which is highly unstable. Moreover, you're trying to remove an electron from a stable configuration, which requires tremendous energy. So that means the second ionization energy will be ridiculously high. So therefore, that disproves option A, and it also says that option D, low value of first ionization energy and high value of second ionization energy, is the right answer. So for the value of ionization energy to increase, you have to remove an electron from a stable configuration. So if you remove an electron from a stable configuration, the ionization energy of that electron will be very, very high compared to the others. And that's why we found that option D is the right option, because sodium has atomic number 11 and 10 is stable. 9 becomes unstable, which is why it forms Na plus ion but not Na2 plus ion. Let's look at this question. Which of the following has maximum energy? So in order to find out which of these has maximum energy, it's just enough to count the number of electrons. So in combination A, we have 1, 2, 3, 4, 5, 6. Number of electrons is equal to 6. In option B, we have 1, 2, 3, 4, 5, and then in the 3d orbital, we have 6. Number of electrons is equal to 6. And then in option C, we have 1, 2, 3, 4, 5, 6, 7. So that means number of electrons here is equal to 7. And for option D, it's 1, 2, 3, 4, 5, 6. So the electronic configuration means that the number of electrons is equal to 6. And among the electrons which have 6, the ones in the 3s and 3p orbital will have more energy, because when you're taking them out, the ionization energy will be more. So this has higher energy, and these two will have lower energies. However, since option C has more number of electrons, we can safely say that option C is the right option. Even though the electrons are present in the 3d orbital, we know that this is stable because we have the half-filled orbital 3p, which aligns with Hund's rule of maximum multiplicity. So that makes this stable. Option C is the right option. Let's look at this question. Which of the following does not have a valence electron in the 3d subshell? Fe3, Cr1, Mn2, Po. I mean, Po, it's actually P0. Po would mean it's polonium, but here it's actually phosphorus. So what is Fe3? This means that whatever the compound which contains this notation will have Fe3 plus ions. And we know that the configuration of Fe is equal to argon, that is 1s2 till 3p6, and then there's a 4s2 and 3d6. So you're removing 3 electrons, so Fe3 plus will give you argon, and then 3d5, because you have to remove 1 electron from here to make this stable, so half-filled orbital, and then you have to remove another one so that it's 0 orbital, and then we have to remove the third one from the 3d orbital. So that gives 3d5 after the solid configuration of argon. So Fe3 plus will have the valence electron in the 3d orbital. One of the 5 valence electrons, are in the 3d orbital. So that means option A is incorrect because it has one in the 3d orbital, 3d subshell. Now, option B, Cr1. Now, this notation means that the ion is chromium plus. So, chromium has the electronic configuration argon, which stands till 3p6, and then 4s1 and 3d5 due to Hund's rule of maximum multiplicity. And we are trying to remove 1 electron, so it makes sense to remove the one in 4s. So Cr plus will give you argon and 3d5. So the valence electrons are in the orbital 3d, in the subshell 3d. So therefore, option B is also incorrect. What about option C, Mn2, magnesium 2? Now this is the same as representing a magnesium ion as Mn2 plus. So this represents the ion Mn2 plus. For manganese, the electronic configuration is argon, that gives us till 3p6, and then it is 4s2 and 3d5. So we have to remove 2 electrons. So ideally, the electrons from the 4s2 orbital are removed. So Mn2 plus will still be argon, and then 3d5. So therefore, option C is incorrect. The right answer is option D, phosphorus 0. So that means this is the electronic configuration of phosphorus, which is 1s2 2s2, 2p6, so that gives still neon, and then 3s2, and then 3p3. So here the valence electrons are in the 3p subshell and not in the 3d subshell. So therefore option D is the right option, and we have proved it by writing out the electronic configurations of all the 4 ions. All the 4 species, we've written down their electronic configurations, and we found that phosphorus does not have a valence electron in the 3d subshell. Now, which of the following statement is correct about ionization potential, which is the same as ionization energy? So ionization energy, there are 4 statements here. We need to find out which of these is correct. Option A states that it's independent of atomic radii. Now this is incorrect. The one thing that we know about ionization energy is that an increase in atomic radius would mean that the electron is far from the nucleus. That means there is less attraction from the nucleus due to the shielding effect. So that means the ionization energy decreases with increase in atomic radii. So this analysis will also disprove the statements B and C, because they are also not true. B says that it remains constant, whereas it does not, and C says that ionization potential increases as we move away from the nucleus, which is also incorrect. The right answer is option D. It decreases with an increase in atomic radii. So option D is the right option. And this is due to the fact that as an electron moves away from the nucleus, it has shielding effect due to the electrons present in front of it. So since electrons and electrons are repulsive, so they provide a shielding effect, which makes it easier to pry off a valence electron as it's farther from the nucleus. When it's nearer, that's not possible. So now let's move on to this question. Consider the following statements. The radius of an anion is larger than that of the parent atom. The ionization energy generally increases with increasing atomic number in a period. And 3, the electronegativity of an element is the tendency of an isolated atom to attract an electron. We need to find out which of the above statements is correct, is or are correct. So let's look at each of these statements. The radius of an anion is larger than that of the parent atom. Now suppose we have, let's say we have magnesium, for example. Now magnesium is the atomic number 12, and therefore it'll be up till 3s2. However, if we have Mg minus, supposedly, so that means it would have 13 electrons. So 1 electron would start filling in the 3p orbital. So which actually makes the new electron being repulsed by the shielding effect. So the radius increases. So the radius of an anion is larger than that of the parent atom because you have to add more electrons into an anion. So that because of the shielding effect between electrons makes the radius larger. So statement 1 is true. What about statement 2? The ionization energy generally increases with increasing atomic number in a period. So as the atomic number increases, so that means the charge on the nucleus increases. So that means we'll have more attraction. So even if an electron is farther from the nucleus, it would still be attracted by the nucleus due to the increasing atomic number. So an increase in atomic number is when there is the addition of a proton. So therefore, statement number 2 is also correct. Now, what about statement number 3? The electronegativity of an element is the tendency of an isolated atom to attract an electron. This definition of electronegativity is false. The correct definition of electronegativity is the tendency of an atom to attract a shared pair. Notice the word, a shared pair of electrons towards itself. And this is evident in water. So the two shared electrons from hydrogen are actually closer to oxygen than to hydrogen. And that makes oxygen electronegative and hydrogen electropositive. So this is the definition of electronegativity, the tendency of an atom to attract a shared pair of electrons towards itself. So statement number 3 is false. So now, after proving that statements 1 and 2 are the correct statements, let's look at the option which satisfies this, and that is option C. Remember, if we were to take A or B as the right answer, then automatically we'll be saying that statement 1 or 2 will be false. Depending on which one is present in the option, the other will be false, which is downright incorrect. And option D will be incorrect because statement 3 is proved false. That's why option C is the right option. It gives you the right statements. Now, let's look at this question. Which is the order for ionization energy that is correct? So which of these ionization or energy orders is correct? So we have an order of elements, essentially boron, beryllium, carbon, nitrogen, and oxygen. So we need to find out which of the order for these 5 elements is the right order for ionization energy. So when it comes to boron, the electronic configuration is 1s2, 2s2, 2p1. If you remove this 2p1, the electron in 2p1, then it would have 1s2 and 2s2. So that will be a more stable electronic configuration. So therefore, boron should have the least ionization energy. Now, what about beryllium? Beryllium has the atomic configuration 1s2, 2s2. As you can see, it's already partially stable. So if you were to remove 1 electron here, then you would require more ionization energy. Next, we have carbon, oxygen, nitrogen. So if we take carbon, carbon has the electronic configuration 1s2, 2s2, 2p2. So if you can take the first two, if you can take the electrons in the 2p orbital away, it would still make no big difference. So therefore, it has lesser ionization energy. However, it would not be as much as the ionization energy of boron. So if you can see, boron, there's only 1 electron left, so it would have a tendency to lose the electrons. But carbon has 2 electrons in 2p, so therefore there would be a lesser tendency to remove those 2 electrons. Now, nitrogen. Nitrogen has the electronic configuration 1s2, 2s2, 2p3. Now notice that the configuration in the p orbital is 3. So that means the orbital is half filled. So when an orbital is half filled, it has stability according to the Hund's rule for maximum multiplicity. So therefore, it will be harder to remove an electron from the half-filled 2p orbital. So therefore, this has the highest ionization energy. The energy which is required to remove one electron from 2p will be greater than the one required at beryllium, because a p orbital has considerably more energy than an s orbital. Now, what about oxygen? Oxygen has 1s2, 2s2, 2p4. So as you can see, oxygen wants to remove one electron so that it gets the partial half-filled stability of nitrogen. So therefore, it would have lesser ionization energy than nitrogen. So therefore, we can classify boron first, and then beryllium. So this is in increasing order. And then we can put in carbon and then oxygen before putting in the heavyweight, that is nitrogen. So therefore, this is the correct order of ionization energy. For ionization energy, this is the correct order. And this order is present in option B, which is correct. Now, notice that in options A and C, they started with beryllium. However, beryllium has a kind of stable electronic configuration, so therefore both of these are incorrect. And in option D, it is said that nitrogen has lesser ionization energy than carbon or oxygen, which is not correct because nitrogen has a half-filled stable orbital. So therefore option D is incorrect. The right answer is option B. Boron, less than beryllium, less than carbon, less than oxygen, less than nitrogen. Now, let's look at this question. The element with atomic number 117 has not been discovered yet. In which family would you place this element if discovered? Now remember that this is 2014, so therefore at that time it may not have been discovered, but now we know that tennessine is there. So it's basically we need to find out where tennessine is present today. So we need to write the electronic configuration here. So 1s2, 2s2, I'm going in from the scratch, not putting in a noble gas and then simplifying it. Just wanted to do it from scratch. So 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and then 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f14, 6d10, and 7p5. So this humongous electronic configuration will be the electronic configuration of an element with atomic number 117. So as you can see, the p orbital only requires one more in order to have a stable configuration. Now, NP5 is the characteristic electronic configuration of group 17, which are the halogens: fluorine, chlorine, bromine, iodine, statin, and more recently tennessine. So therefore option C, halogens, is the right answer. Now, why options A, B, and D are incorrect? Because A means alkali metal, so it has to end at 7s1, which is not there, so option A is incorrect. For alkaline earth, it has to end at 7s2, so which is also incorrect. For noble gases, this has to end at 7p6, that is the atomic configuration for oganesson, which is not there, which is not the one which is present here, because we are looking for tennessine and not oganesson. So option D is incorrect. The right answer is option C, halogens, because after doing the electronic configuration, we got the result. The last one is 7p5, and NP5 is the characteristic electronic configuration of group 17, and group 17 contains the halogens. So the element with atomic number 117 is a halogen. Now, let's look at this question. In which of the following arrangement the order is not according to the property indicated against it? Now, lithium less than sodium less than potassium less than rubidium, increasing metallic radius, iodine less than bromine, less than fluorine, less than chlorine, increasing electron gain enthalpy with negative sign. B less than C, less than N, less than O, increasing first ionization enthalpy. Al3 plus, less than Mg2 plus, less than Na plus, less than F minus, increasing ionic size. So we need to find out which of these has the right explanation to the order given. For option A, lithium less than sodium, less than potassium, less than rubidium, and it's given increasing metallic radius. So as we go down the group, the size increases. So therefore, the metallic radius of group 1 will increase as we go down the group. Lithium is at the top, rubidium is at the bottom, and sodium comes after lithium, potassium comes after sodium, so therefore this order is correct. And that's why the option becomes incorrect. We need to find which of them is not according to the property. Now, what about option B? Iodine less than bromine, less than fluorine, less than chlorine. And the reason given is increasing electron gain enthalpy. So electron gain enthalpy increases in negative sign as we move up the group. However, there is an exception in the first case, fluorine and chlorine. It is said that chlorine has more electron gain enthalpy than fluorine because of the p orbitals present in it. It is present in the 3p orbital, and F is present in the 2p orbital, so there is an increase in energy at chlorine than fluorine. So that's why it has greater electron gain enthalpy with the negative sign. So therefore, this order is correct. Chlorine has the highest electron gain enthalpy, iodine has the lowest. So option B is incorrect because this order is correct with regards to its property. Now, what about option D? Al3 plus, less than Mg2 plus, less than Na plus, less than F minus in terms of increasing ionic size. We know that anions are larger than the parent atom, and the parent atoms themselves are larger than cations. So Al3 plus implies that 3 electrons are lost from aluminum. So that means we have a greater amount of protons than electrons, so therefore the atomic radius will be small. And similarly with Mg2 plus, 2 electrons are missing, so there'll be greater atomic attraction from the protons. So therefore Mg2 plus is also small. Na plus is also small because of the same reason, and F minus, which means it has an extra electron which reaches stable electronic configuration, would imply that the anion would have more electrons, so therefore more shielding effect, so the anion increases in size. So increasing its ionic size is correct because anions are usually larger than their parent atoms, and the parent atoms are usually larger than the cations. So option D is incorrect because this order is according to the property indicated. So the statement is correct, which makes the option incorrect. So that means our right answer is option C, B less than C, less than N, less than O, increasing first ionization enthalpy. This is not correct. If we're looking at increasing first ionization enthalpy, then it should be B less than C, less than O, less than N, because nitrogen has half-filled orbital, which makes it more stable than oxygen, and it makes it more stable than carbon because it has 2p3. So therefore, option C is the only option where the order is not according to the property indicated. So that makes this option correct because the statement by itself is not according to the property indicated. Now, we need to find out the correct decreasing order of first ionization enthalpies of 5 elements of the second period. So how do we do it? So here beryllium is 1s2, 2s2, boron is 1s2, 2s2, and then 2p1. Carbon is 1s2, 2s2, 2p2, and then nitrogen is 1s2, 2s2, 2p3, and then we have fluorine 1s2, 2s2, 2p5. So the atomic size will decrease as we move across a period, and therefore the first ionization enthalpies will decrease accordingly, with the exception of nitrogen, of course. So therefore, we can state that nitrogen will be greater than fluorine, but that would not, yeah, nitrogen would be greater than fluorine, which would be greater than carbon, greater than boron, greater than beryllium. So here, beryllium has 2s2 completely filled, so it's more stable. So boron has to be last. And the only one in which boron is the last is option C. So over here, we're given the decreasing order. So that means the last element would have to have the lowest ionization enthalpy. And in case of ionization enthalpy, we know that boron is the least because it has one electron to be removed in order to gain beryllium's electronic configuration. So therefore, we can say that option C is the right option just by looking at which has the lowest ionization enthalpy. So boron has that, and the only one with the option is option C. So that ends this episode of NEET preparation. So this chapter is very short. However, there are other chapters such as structure of atom, which are extremely long. So we've made dedicated episodes for the chapter structure of atom. So if you want to view that, then you can just click in the link on the description down below. I'll be providing a link for the playlist of NEET chemistry from which you can access all of our videos. So that can help you in preparing for chemistry. Now, if you want to access more of our useful and interesting content, such as learner words, mind maps, memory hacks, English lessons, the International Phonetic Alphabet, etc., then please subscribe to our channel, Brain Blitz Audios. To receive notifications about our latest content, don't forget to click that bell icon, which is the notifications button also. So until the next episode, take care, stay safe, bye-bye for now.